Our first speaker this morning is going to tell us about this title. It kind of amazes me, the idea that it could be on a pathway toward designer Hamiltonians, one atom at a time. But Craig will explain all of that. Craig Fennie of Cornell.
Thank you, David. Yes, the title is supposed to conjure up lots of exciting imagery and images and get you to think about the possibility of actually doing this, right? My pleasure to be here. What I want it to do today is to tell you a little bit about that title and this challenge of designer Hamiltonians within the context of materials design and complex oxides. I then want to, this is a very broad challenge, something that I'm incredibly interested by and consumed with, is that first thing there. But we'll try to narrow that down a little bit and give you some ideas on how one can go about designing materials to be realizations of Hamiltonians, a sort of design strategy. And then we'll narrow it down a little bit more and give you some examples of where, unfortunately, not necessarily Hamiltonians, but classical microscopic models, starting with a model, microscopic model, how these things interact with each other, we can end up with a material realization of that within the context of these magnetoelectric multi-fluid materials. And I'll probably end there, perhaps one intriguing slide. The last bullet point of can we actually use these same ideas to control the metal insulator transitions. So what is this big challenge that I'm talking about here? What it has to do with Feynman's last blackboard. I found this image recently. It's much nicer than my handwriting, but still perhaps not necessarily clear. So I'm assuming this is a pointer. Yeah, good. Okay, so we have lots of things written here. This one right here is know how to solve every problem that has been solved. I've had peers for 3 graduate courses and not time for one. I'm sure they can tell you that probably isn't the case with me. Probably not something I'm going to ever be able to do. Learn data onsets. Again, not time will probably stop us right there. That's probably not the case. But this one up here is perhaps, this is one that intrigues me. It says, what I cannot create, I do not understand. I've heard this phrase in several different contexts. One that what I cannot compute, I do not understand. What I cannot calculate, I do not understand. But I never realized the original quote was, what I cannot create, I do not understand. This sounds a bit strange, right? Particularly with our usual approach to creating new materials and discovering new phenomena, right? Let's take a little bit of a detour, and I love cartoons to really illustrate points. What is our usual approach to discovering new materials and new phenomena is best described by these 2 people here. This scientist here is trying to develop this brand new product that's going to revolutionize the company. It was a total flop. They were going after an insect repellent, but however, it's a killer acting drug. Materials, new phenomena are usually discovered completely by accident. One more related to my field is this. It was interesting to see in the New York Times a few years ago that this happy accident chemist produced a new blue. Master Brahmanian, a friend of mine, a solid-state chemist in Oregon State, discovered this new blue pigment. Blue pigments, I'm told, are expensive and usually rather poisonous. This one is none of those. It's an oxide material. It's quite benign. In fact, he is now just not only made blue, he's making every color in the rainbow out of this material. It is actually starting companies. It's revolutionizing the paint industry. Mass, as some of you may know, has worked a lot on sort of correlated electron phenomena, superconductors, blah, 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 multifluidics. In fact, he was going after a new strongly coupled multifluidic, this yttrium manganese oxide. In fact, doped with this indium, but that's not really important. The doping was supposed to make this the world's best multifluid. It was terrible in terms of its magnetoelectric properties, but they discovered Again, things are discovered by accident that change, that lead us to new places. And so really, the usual approach that we're seeing is that new materials are discovered. Properties that we wouldn't expect them to have are measured, and we try to work out what they mean and to try to understand them at a very deep level. I see this challenge that we have is, can we start with some Hamiltonian? And here's just an example. It's quite simple and doesn't really matter what I have written here. The point is, it's just a Hamiltonian. Can we start with this Hamiltonian that we've solved in some way and we can qualitatively describe some macroscopic phenomena with? Then we go from that to a real material. And that is the question that I have been obsessed with. And we've briefly, in the last sessions, heard these words already: Materials Genome Initiative. These are a lot of buzzwords, materials by design, blah, blah, blah. But as some of you know, and perhaps all of you know, the White House a few years ago had this idea that we have this genome initiative where we sequence everything and we learn all about biology this way. Can we do the same with materials? Can we compute every material and every structure and with every chemical species, and somehow this huge amount of data is going to teach us everything we want to know about materials, and all the discoveries will magically pop out. In this context, though, materials design and discovery mean different things to different people. One, I like to break these up into very extreme views. One is, if I'm just given ABX, what crystal structure could be synthesized, or perhaps a more practical question was simply the equilibrium ground state. Very interesting question, but more related to the context of this idea of designer Hamiltonians is another way of thinking about materials design, is that what specific elements, for example ABX, and what arrangements in space give me some property or functionality that I'm interested in. And as long as one can find a meta-stable structure, the question then turns around, not necessarily, the question turns around to being not what material do I really need, but how do I stabilize this metastable structure. Put this in a little different context. We're up here. We're starting with some effective microscopic theory. How do we find material realization? The first step, and we'll show some examples of this later today, is we come up with some materials candidates. How do we go from that step of the theory to the material candidates? There's a lot in there. And the examples that I'm going to show you, it really rely on physical and chemical intuition. How do we construct at the level of atoms and arranging atoms in space? How do we find those motifs that allow the interactions of a microscopic theory? How do we then build up those motifs into an extended structure? If we have no chemical intuition about the system, or physical intuition about the system, how can we generate that? We heard a talk yesterday, a Jacqueline, great talk, of a way of doing that. We could perhaps data mine known structures, or we could perhaps compute unknown structures, or chemistries in unknown structures, and mine those as well. So data mining, these inference maps, all of these computational techniques are great ways of developing chemical and chemical intuition where none currently exists. But once we have these realizations, we can then turn to our first principle quantum mechanical techniques to see if these material candidates really are realizations of this microscopic theory. And the final step I've left here often question marks, because in some cases you can run and you find that structure. You find that material that is the realization. Most often, in my experience, that structure is not stable, or it would have been found already by some chemist making it. It's usually metastable, and the question then does turn, how do I stabilize that metastable structure? More often than not, finding this last step is a little bit more tricky than finding this last material realization that can actually be made in the lab is a little bit more tricky than one can imagine. And in my mind, a lot of times, material itself is not necessarily the end game here, right? The design rules, if we could theoretically get at a set of chemically intuitive design rules to then take to our chemist friend and work with them to find this material and realize it in the lab is really the goal of our theory. And just a little play on words here, you know, the design rules are good enough. Imagine deriving good enough kind of motor rules from first principles. That's a very powerful, simple set of rules that help us find material organizations. All right. Materials that I'm interested in, I was told this was a very broad audience, and I'm assuming, and I'm realizing it's probably not as broad as I once thought, but I'm interested in rocks, right? Complex oxides, or rocks. One of the most interesting set of complex oxides, the perovskites. Here's the actual mineral, calcium titanium-3. Perovskites, silicates, the most abundant mineral in the lower mantle. Our rocks tend to look more like this, or at least the insulating rocks that we play with. Yeah, they are pretty rocks. All clear though, so still no electrons in the problem. That's another talk. But here is, perhaps in my mind, the simplest example of a complex oxide. The perovskites, which I mentioned on the previous slide. It's simple in the sense that the prototypical structure seen here is relatively simple. It's a cube. Can't get much simpler than a cube on a lattice. There's only 5 atoms in this prototypical structure. It's an ABO3 compound. A sits in the corner of the cube. B sits in the center of this oxygen octahedra. The octahedra are corner shared, and there's a 3-dimensional network of these octahedra. They're complex because small changes in the chemistry lead to vastly different properties. The properties alone display just about every known physical property that exists in nature. Adding to the challenge and the opportunity in these materials is that just about the entire periodic table, in some way, fits into the structure. So these color codes are supposed to suggest that just all the transition metals, these blue things here, can fit on the B site. All of the alkali metals, all the alpha earths, the anthracites, they all fit on the A site. You can have multiple cations on the A site, multiple cations on the B site. You have an enormous number of possible compounds that can exist in just one structure. If you think about the various size differences of these primarily ionic cations and anions, you can question how does this one structure accommodate all this chemical diversity. It's that this idea that we have this cubic perovskite is a bit naive. Very few perovskites actually form a cubic structure. Most of them, in order to accommodate all of these different cations, distort. The octahedra distort in various patterns. 2 common patterns are that these rotations, or that these octahedras rotate. The 2 most common ones here is one pattern known as the orthorhombic perovskite structure. Here is a multihedral distortion, or multihedral distortion of the octahedra. And it's because of these rotations that we can accommodate all of these different cations. The reason why I'm harping on these very subtle and a lot of times small structural distortions is because, believe it or not, these very subtle distortions control the properties of these materials. Here I'm just showing you 2 phase diagrams of 2 examples. I can show you for just about every transitional oxide a diagram like this. This is a rare manganite, this is a rare epiphyllite from the bottom. What we're seeing here is temperature versus some parameter, which I'll mention in just a bit. The dots refer to different compounds, from lanthanum all the way down to holmium in this case. These are all 3+ cations, and these are all 3+ cations. These are isovalent substitutions. We're not adding or taking away electrons, simply changing the size of the cation on the A site. And what I'm showing you over here is the manganese oxygen bond angle for this top graph. So that is the angle between the atom here. Let's say the manganese atom here, the oxygen and manganese. If this was a cubic structure, this would be 180 degrees. As we make the cation on the A site smaller, this rotation increases. As you can see here, if we make the cation smaller, the rotation angle decreases more, sorry, deviation from 180 degrees increases more and more. Rotations becomes larger. What I'm showing you down here, it's plotting versus tolerance factor. Just know that way of plotting that. The tolerance factor is a geometric descriptor. Imagine that we have this cubic cross-hatch structure. Just imagine you pack these as hard spheres. The ideal packing of hard spheres would lead to a tolerance factor of 1, but if the A site was much smaller, this tolerance factor would be less than 1. Chemically, that means that the A site is, its bonds are very unsatisfied. The crystal structure will want to distort in order to accommodate the chemistry of its A site bonding environments. And that's what we're doing here. As the A site gets smaller, the tolerance factor gets smaller, and the system distorts more and more. These very subtle rotations completely control the correlated ground states of these materials. You can completely tune between different magnetic states in this rare magnetic case. Completely tuned from this is the lanthanide plate as a metallic phase all the way to an insulating phase just by changing the rotation angle, the rotation patterns, et cetera, et cetera. These small distortions are key to understanding and controlling the properties of these materials. Recent advances in synthesis allow people to make these materials one atomic layer at a time. Techniques known as molecular epitaxy or laser PLD or off-axis sputtering allow these beautiful materials to be made in structures that don't exist in equilibrium. You can imagine making superlattices such as the one shown here. Here's some high-res TEMs of various structures. This one here, the center one is perhaps 10 years ago or so, really ignited this field of complex oxide interface and interface physics in complex oxides, because this is an example of taking two materials that are both lanthanum titanate and strontium titanate, which are both insulators. And by making this digital superlattice, by making active interface between these two insulators, this is a non-insulator, this is a band insulator, two-dimensional electron gas emerged. This is a great example of what one can do using these techniques. And so more is definitely different in the field of complex oxides. There's just an enormous number of possibilities of things to do with these materials. As a theorist interested in material design and predicting new phenomena, discovering new phenomena, that's a challenge. How do we get a handle of all of this enormous, and I hate using this word here because, but I will, complexity of the problem. And again, cartoons, I love cartoons, and I hope you like joking in the morning. But this has really led to a typical experimentalist view of theory predictions. Here's two experimentalists sitting around the fire and say, yes, it's a wonderful discovery, theory discovery, but whatever you do, don't touch it. Times are changing, right? There are new theoretical methods, new theoretical techniques. I'm not going to talk about them. That's not really relevant for the points that I want to make here. But also new ways to think about materials design. That is what I want to talk about. I view these experimental, huge leaps in our experimental capabilities of making and characterizing these materials as an opportunity. An opportunity to control, again, this word is popping up everywhere, structural complexity of this problem. We can put atoms where we want to, right? By putting atoms where we want, we can control the interplay of these various microscopic degrees of freedom, the charge, the spin, the orbital degrees of freedom, and produce and control the macroscopic, observed macroscopic phenomena. What I'm going to show you today is how we can manipulate the structure, put the atoms where we want to control the, again, sorry, this is a little out of but anyway, control the interplay of microscopic freedom. But what really I'm going to do is to start with the Hamiltonian or something like this, and describe what this is when we get there. But again, we have this Hamiltonian. We're going to place atoms. We're going to find those structural motifs that allow us to control the interactions, that's these J's and D's here, to produce new phenomena that doesn't exist. Right. Sorry. Getting a little too excited. In fact, we're going to design structures in such a way that these parameters are controllable with an electric field. So we have a Hamiltonian. We need to find a realization with that Hamiltonian. We're going to, this realization, we're going to construct in such a way, atom by atom, such that these parameters of our Hamiltonian are controllable with an electric field. All right. More specific challenge. Can I design a general materials platform for which an electric field couples naturally to different correlated ground states? What I mean is, for example, can I take an electric field and turn a ferromagnet into an antiferromagnet, or vice versa? Since most complex oxides are antiferromagnetic to begin with, it would be really cool if we could take an electric field and take those spins that are pointing like this, make them all point in the same direction. We also do the same thing in control metal and state transition. Can we design a general platform where both of these things are realizable? An approach that I love to think about to really produce this coupling, these strong couplings to external fields, is based on an idea that's pervasive in materials physics: phase competition. Here's 3 different phase diagrams. Again, it's not too important what they are. This one is a magnetite. This one is PZT. It's a lead, zirconium, titanium 3. And this one is a solid solution of terbium iron 2 and dysprosium iron 2, known as terphenol D. This one displays a colossal magnetoresistive response. This material here is displays what we call a colossal electromechanical response. It's the best known piezoelectric material that exists. And this one is our best known colossal magnetostrictive material. The underlying universality of all of these things is that where these large responses occur are right in the vicinity of these vertical phase boundaries shown here. So the idea is that one tunes to a phase boundary, and in the vicinity of these phase boundaries, we have these large responses. So can we tune to a boundary and take advantage of these various phases that are competing to produce sort of large and colossal responses? Very schematically, what's going to be key to everything that I'm thinking about in order to take this electric field and have it couple to the underlying degrees of freedom is the idea that underneath, in this material that we're creating is a ferroelectric. In fact, the starting point is to start with material that is a paraelectric and design a way of controlling this paraelectric and ferroelectric transition. And we've seen examples before in this PZT. That's exactly what's going on. We're using chemistry to do this. We don't want to introduce any disorder. We don't want to just make random alloys. We want to find new control parameters in order to tune to phase boundaries. But then, we want to add to the problem other degrees of freedom. So imagine that we start with a material that is paraelectric and has property 1, and we can define some control parameter that if we were able to tune this parameter, we'd be able to tune to material that's ferroelectric and has a different property. And so we have to come up with ways of coupling all of these different phenomenological properties, these phenomenological order parameters, if you will.
Question.
Yes?
This property 1 and property 2 are completely unrelated to the parallel property.
Exactly. So here's an example in the next slide, or 2 different examples. Property 1, imagine this phase, it's in example 1, and this is what I'll talk mostly about today. Property 1 could be paraelectric and antiferromagnetic. Like most complex oxides with magnetic degrees of freedom are antiferromagnetic and paraelectric. Let's start with one of those and come up with a way of tuning to a phase that is ferroelectric and ferromagnetic. In another example, you can imagine taking a paraelectric metal, and somehow, this is, I don't want to get too bogged down jot down now. We can come back to it at the end of this time. This is what I'm really, really excited about today. Imagine paraelectric metal and coming up with a way of tuning to a phase that's ferroelectric. In other words, it has to be insulated. So now you're coupling a paraelectric metallic phase to a ferroelectric insulating phase. You couple the metal insulator transition to a system that has a polarization and one that doesn't. You're coupling all of these degrees of freedom. There's a chance, and it could be a way of controlling that metal insulator transition. Field. What's that? It would be a non-insulator, yeah. Right, so actually all of these systems are non-insulators that we're talking about. In this first example, and this is where we spent a lot of working on, these are non-insulators that are very far into the non-insulating phase. They're very good these are very good insulators. Very far from the transition. Whereas these bottom ones you can imagine being much, much closer to the regime where correlations and everything becomes much more interesting and much harder to describe. Yeah.
Really basic question.
Sure.
How would you define non-insulators in your circle?
There's at least 5 people in the room who could do a better job of that.
No, I think they're doing a great job.
Okay. So how I would describe it is a very naive view. My naive view is that, and there's just caveats and blah, blah, blah. Let's forget all about that. Very basically, to an experimentalist, first shot, a non-insulator is a material that is insulating, yet band theory would predict it to be a metal.
Yeah, okay, I have the same problem.
It's very unsatisfying. There's, particularly when you get closer and closer to this transition, you have no idea what's really going on.
And with all your experience, could it, what insulators can be dealt?
This is.
These are hard questions. I'm sorry.
No. This is. So, in the past 6 years, I've worked on this problem a lot, and that part. Sorry.
No, I'm saying.
Oh, okay. It's good to hear in the middle because I always get kicked out by silence. I did do my PhD at Rutgers where, that was not, that had never happened.
I was so quiet and shy at Rutgers.
Yeah, your first slide you could spend half your talk on. I was at this. This is where I'm heading. That's the sort of questions that I want to learn more and more about, and one of the things that I'm trying to reach out to the broader community to start discussion. How do we do this? How do we figure out how do we do it? And this one is a little less interesting from that perspective, but much greater.
But that's a quick question on that, right?
Yeah,
if you ask me the question, can you predict which ones? Then you cannot.
I can
tell.
The best that I would ever, but I have not thought hard about this problem yet, but my guess is that I could not.
Most of them don't go, right? You just can't go.
Yeah. Fortunately. Yeah. That's the question. But the idea, not to get too distracted, just to follow up on this a little bit.
About getting distracted in the middle.
But
it's good.
Okay. Is that a fundamental? Again, this more and more that we're learning about non-insulators is that correlations are incredibly important, but so is the structure. And the structure has been almost ignored today. If we could focus on that problem, try to manipulate the structure to get closer and closer to this boundary between the metal and the insulator, then these sort of questions of can we dope them, can we actually control these transitions, and so forth. I'm hoping that in a very nice way that it becomes easier Structure is a very important part of it, and we almost, as a community, have ignored it today.
Maybe this is maybe more of a rhetorical point, even in response to this, I don't want to keep this on, but, and also may reflect the fact that I've got sort of now strong correlations for 10 years or so, but it still strikes me, and correct me if I'm wrong, I don't know of any examples of real experimental isolators, so there's not a broken symmetry. So that you can also, once you form the isolated state, you can also see that there's the electron counting works out. So that the fact that it's both, it is an insulator also. Once the symmetry is broken, it's an insulator also. But I'm willing to be proven wrong about that. Jim?
So the real issue is whether you're forcing yourself to discuss this at t=0 or not.
Yeah. Yeah, I'm talking about T=0 there, right?
Yeah. So you take the pi phase of B203 was always said to be the famous example of a real mod insulator, because then I wasn't magnetic and it still was an insulator. But I think conceptually you can't take the pi phase of B203 all the way to T=0, because what do you do with the entropy? You just, as a simple-minded way to put it, then you got a bunch of magnetic moments, and if you're not going to order them, something's got to happen. And so then you're into issues like spin liquids and topological order and stuff like that. So I think that's the deep philosophical question, or not philosophical question, but the deep theoretical issue is exactly that. And that's, I think, the issue that Bob Laughlin's been raising in these arguments with Phil Anderson probably. Exactly that, whether you have to be a T finite T or not, and if you have to be a T=0, you can have it there as that a real phase of matter. And those are the kinds of issues under discussion.
And now we're still like, get back to the flow of this talk.
Yeah, I don't know how to follow that. All right, it's like, first we're starting about consciousness, and then like, wow, I gotta get out after we just talked about consciousness. All right, yeah, good. So, yeah, these properties, one property two are distinct from parallel to parallel. Going right back in line with the question you asked. Let's talk a little bit about this example. And this is, again, in the context of, I think, what I was asked to talk about in terms of multifunctional. For those, we heard a big talk yesterday from Sean Chit about multifunctional. I won't say too much more, except to realize, or again, just introduce definitions. Multifunctional is a material that has a spontaneous electrical polarization and a spontaneous magnetization. The goal in this entire field of multifunctional is, to get back to step, these are inherently multifunctional in the sense that an electric field couples, in the sense that they respond in a useful way to more than one. I don't think any of them could be made, but from those and from the energetics that we're learning, we've incorporated all of that information into and refining these rules to help us better find that right material. So the short, may or may not answer your question, but fundamentally I believe that materials, finding that actual material in the lab is so much better done by the person in the lab making that material. And that the theorist really, if they do their job right, really gets that experimentalist and all their chemical intuition, focusing them really in the direction of where to head and where to go. So I'm not, with that, I'm wrong.
So you're proposing that we be motivational theorists. I think you're right. I'm listening to your talk, and I'm summoning up Barrett Matthias, who's the great material scientist of the middle part of the last century, focused initially on ferro electrics, went off to superconductivity, and of course has left us as his major heritage people like Zach Fisk, like Paul Hanfield, etc. There you are.
Sorry, finish your point, sir.
Barrett would have been fascinated by the structure rotation that you said. He would, on the other hand, not have come to your talk if he thought it had anything to do with Hamiltonian
So, yeah, this is what I love. I used to have my talks like this, but you always have to reinvent your jokes. But since maybe it's been so long since I said it, let me end here, since you did a nice segue to this. These were his rules for discovering high for new superconductors. Symmetry is best, peaks and densities are good, stay away from oxygen, stay away from magnetism, stay away from insulators, stay away from theorists. It is questionable 1 through 5, so maybe 6 is...
Actually, right after BCS, and Barrett was not a fan of BCS. I then was able to show a very simple calculation of how the basic idea of BCS, the electron, the Fermi surface development, how that could explain Matthias's rules. Matthias was a good friend, and I paid a lot of attention to what he said. And he gave a party to me. Other questions, comments?
Let me try one more, and that is that lately there are lots of even more complex perovskite structures, things where you fool around with ananias and order rocks and nitrogen and disorder, when you start putting in the ones that really fascinating phase, you start putting in large complex ions. Things like that. Does that give you additional variables for your game?
Yes. And I could talk for a few more hours on Rodelson Hopper's, Dion Jacobson's, and how we can use. So one of the ways of creating these functional rotations is by layering A-site cations in simple perovskite. Essentially, what you're doing is trying to break this conductivity without really breaking it. So why don't we just go to systems where we really break the conductivity by shoving in large atoms? So imagine having a two-dimensional layer of perovskite, shoving a large atom, and another two-dimensional layer of perovskite or something. These things naturally form, as you know, one structures known as Dion Jacobson, others are known as Rodelson Hoppers. The group breaks themselves with n equals 1 Rodelson Hopper. The n equals 2 Rodelson Hoppers actually can be made ferroelectric using this technique. We can do layering of things, and yeah, I think that what I've shown and what I've talked about today, from the structural, from the solid state chemistry point of view, is sort of the baby step. And we've been thinking about more interesting ways of doing this from the solid state chemistry perspective. And I'd love to tell you about this.
I have a question. How many anti-ferroelectrics are there?
That is easier said than, okay. So the question is, how many anti-ferroelectrics are known? And one has to, Jim Scott's not here, so I can, I would say 0. I think that's the simplest answer. There's caveats and more discussion, but I think from a starting point, if we start with 0, I think I won't be too far off. Why? It's a great question. So what does an anti-ferroelectric mean is even a better question. Because this whole idea that the simple Cattell model of an anti-ferroelectric is I have a small dipole in this unit cell and another dipole pointing in the opposite direction in this unit cell, and they alternate, right? One up, one down, one up, one down. The whole notion that we have localized dipoles in an extended system doesn't exist, right? Very phase theory of polarization is taught us that. So the whole notion of what really is an anti-ferroelectric is kind of complicated. And I don't think, well, people are trying. Perry Ray has done a really good job recently of trying to define what do we mean by one?
So we should go back to the plan and can't create it and don't
That's all right, yeah.
So that question actually more detail. So you have this parameter J and P in the model. Is this something you can calculate, or can you give us an idea of what to expect? Because I think that that's important.
Sure, no, we can calculate those and we've done
So how do we compare? Is that what you expect?
about a tenth or so in one case. Usually they're about, D's are always about a tenth or a hundred.
So you would think that that is small, right?
They're kind of small, right?
So that it's very small that you will get all of this canceling and stuff that happens.
So I didn't talk about any numbers here.
Yeah.
But the sort of numbers that we're seeing are perhaps canting in some of these systems at largest about 0.1 per megaton. About largest, usually about half that. And that is what has in these iron titanium 3 and compounds like that in this lithium niobate structure. That's sort of once they were calculated, and they actually should be. These things shouldn't have worked out well, but these are small. But right now we're still trying to figure out how to couple these things. And small moment, switching 180 degrees versus not having any examples it's measurable. That's the main thing, they're measurable. And
Mark was very inspiring. But one of the problems I have with your talking about my colleagues at Focus is that they focus an inordinate amount of effort on systems with no electrons.
yes.
And these are wonderful control devices. But what are the prospects for adapting this general approach to the systems we develop?
Great question.
Why don't you repeat it so the audience can hear it?
Certainly. There are no electrons in my system, and people love electrons. More seriously, the systems that I'm working on are band insulators or Mott insulators. What are the prospects for taking some of these ideas of conformal structure and moving them into regimes where the electrons are, correlation of electrons are really the problem. And so sometime this week, the trustees will vote on my tenure case. And after that, I can move from problems I know a lot about to problems that I know very little about. To help that, in fact, Bernard Kim and I recently hired our first joint postdoc. And you know what else? So she likes electrons. We're moving in that direction. This is why I'm happy unless I don't understand. And I don't understand anything about that, but a lot of the physics. And I want to see how well we can control those types of interactions of the structure.
We should have a go, I think, and then we'll go for a break, and doing an ICAP workshop connecting all the things you've been saying to the electron control systems, and there will be many examples from heavy electrons, big weights, etc. Things that look just like that, the superconductivity emerging as a maximum, right at the border between anti-thermal and itinerary behavior.
This is why I'm here. This is why I want to learn more about it. I want to make more.
I think trying to bring those two communities together would make for a neat workshop. I'll nominate you as one co-organizer, and here is an